we are going to review just a couple of slides from last time, because for those who weren't here last time or who may have forgotten, they're kind of a basis for some of the things we're going to get into today. And this is part 2 of the getting the most from your electric motors. We will have part 3 next week, and then we'll move into other things. We've got several VFD seminars planned. We've had a lot of requests for troubleshooting and maintaining VFDs. We'll be getting into that. So let's start with our motor temperature rise. This is a review from last time. Typically motors come in B, F, and H insulation. Now if you've got an old U-frame motor, that U-frame motor may have had a temperature rise of 55 degrees C. And so a lot of people think, boy, those U-frame motors, they were really good because they run so cool. Well, yeah, they do, but they are also very large and pretty expensive. So these days, typically most motors contain Class F insulation, and Class F insulation is rated for 155 degrees centigrade. So that is 40 degree ambient plus 105 degree rise plus a 10 degree hot spot. And as we mentioned last time, the hot spot basically says that there's somewhere in that motor that's going to be 10 degrees hotter than the average temperature inside the windings. So you just add that for a little bit of conservative calculation there. So that's 155. Now a Class B motor was good for 80 degrees C rise, and that gave you a total temperature of 130 degrees C. As we mentioned, it's very, very common, and I highly, highly, highly recommend it to specify a motor that has Class F insulation but Class B rise. In other words, it's got the good insulation capable of 155 degrees C, but it will not run at more than 130 degrees C. Now, Class H, a lot of motors, in fact, most motors have some Class H materials in them, but if you want to have a motor that's actually stamped and nameplated with Class H insulation, that's going to be a significant premium, and I don't see any point in doing it in most applications. Now, if you have applications in which the motor is in a furnace or something where it's really hot, then yes. But typically, you don't want to run motors that hot. Even if the winding insulation can handle it, you're probably going to have bearing and other problems. So these are the types of motors, and on the left, of course, is just a stainless steel motor. Those are used in washdown applications, primarily in the food industry. But these are the 3 main types of motors. This one is a open drip proof with a steel frame. This one is an open drip proof with a cast iron frame, and this is a totally enclosed fan cooled. I'm going to spend some significant time on those in just a few minutes, so I'm going to move on at this point. Now, this is a totally enclosed fan cooled motor, and you can see that the air doesn't actually go through the motor. The air goes over the outside of the motor. So it comes in through the end bell here. It hits this fan, which is on the shaft of the motor. That fan is a centrifugal fan, which forces the air towards the outside, and then it goes over the outside, and you can see these fins molded into the cast iron that helps the cooling of that motor. Now, the question is, number one, where is the hot spot, and how hot can a motor be? If you have temperature measurements inside the motor, that of course is wonderful, but most people don't do that on these little small motors, just simply due to cost. So where is the hot spot, first of all? Well, we typically say that the hot spot is in the iron right here in the windings. And so we would put a temperature measurement device, if we were going to put one in the motor, in that location. Now, it is possible that sometimes the hot spot is out here on the end turns. And so right there's your end turns. So that's possible, but typically we put it in here. Now, if you don't have a temperature measurement device, is the motor too hot or is it not? Well, here's an open drip proof motor. On the upper left here, the air goes through the motor. And because the air pretty much is between that outer frame and the inner rotor, it's very difficult to determine whether that motor is overheating by simply feeling or measuring the outside temperature of the motor. So unfortunately, we're kind of lost there. On a rolled steel frame motor, that that frame is in good contact with the outer steel frame. You have very quick thermal movement of the energy to the outside. And typically, these types of motors will have a surface temperature that's 10 to 15 degrees below the hotspot temperature. So if you measure the temperature on the frame of that motor, and then you add 15 degrees, that's a pretty good indication of how hot the temperature is inside the motor. Now, most really good quality industrial motors are totally enclosed fan cooled. And in this case, the motor may be 15 to 25 degrees below the winding hotspot temperature. So again, we can take our infrared gun, we can measure the temperature of the frame, add 25 degrees to that, and that's a pretty good indication of what our hotspot temperature is inside of the motor. So I think that's good information to know. Now, my rule of thumb for many, many years has been put your hand on the motor. If you can hold your hand on the motor for 3 seconds, then the motor is not too hot. Other than this open drip proof cast iron motor that I showed you before, that's still a pretty good rule of thumb. But if you can't keep your hand on the outside of the motor for 3 seconds, the motor might still not be too hot. So let's take a look. The typical human can tolerate about 60 to 65 degrees centigrade. Let's suppose we have a motor. It's operating at 65 degrees C rise. And remember, even a class B rise is 80. On a hot summer day of 35 degrees, and remember the rated temperature for ambient is actually 40 degrees. So we're not anywhere close to the maximum rating of that insulation. The winding total temperature is 65 plus 35 is 100 degrees centigrade. Take 20 degrees off of that because the frame is going to be 20 degrees or so cooler than the inside. And that means the surface temperature will be 80 degrees C. And we just showed you that you can only tolerate 60 to 65. So my point is, if you can keep your hand on the outside of the motor for 3 seconds, in a totally enclosed fan-cooled motor or in a rolled steel frame type motor, the motor is not too hot. If you can't keep your hand there, it might still not be too hot, but that's the point at which we need to measure the temperature and do a little bit of calculation. A little harder than just sticking your hand on a motor. Now here's your thermal life curves. And I think this is kind of academic. They say that for every 10 degrees increase in temperature, then you will decrease your insulation life in half. But normally we're not running at these temperatures. And in fact, thermal degradation of motors is almost never the mechanism of failure of a motor. So it can be, absolutely can be, but typically it is not. And so this is interesting, but I don't spend a lot of time looking at those thermal life curves. Now, how can you measure temperature? Well, this is called a Clix-on. It's basically a thermostat. Works just like the thermostat in your house. When it gets too hot, that little contact in there will open, and you can buy Clix-on devices in many different temperature ratings, depending upon at what point you want to stop the motor. So in this, whenever that Clix-on opens, you are going to put it in the control circuit and stop the motor. And it's up to you to decide what temperature rating you get. We're going to talk about that in just a moment. On our heavy-duty industrial motor that I will talk about in a minute, we give you a standard Clix-on, but most motors do not have that. This is the information that came on a Clix-on data sheet, and I am not going to go through this too much because there's a lot there, and when you actually get to this, you're never going to remember it anyway, so pull out the data from the Clix-on. But they will tell you what temperatures they recommend that you buy, and they're saying down here maximum allowable temperatures for an integral horsepower motor with Class B insulation is 165. Well, that's awfully hot. And so generally we would probably put that down much lower on the range of maybe 130. But this is what the Clix-on data sheet says. And sometimes they put these a fair amount above the rated temperature because they don't want them to trip. Now this is a thermistor. I don't see thermistors much in American motors, but we do see them a lot in Asian motors particularly, and somewhat in European motors. A thermistor is a solid state device like a transistor or a diode. It's and you can see the picture of one, and it has a very non-linear temperature characteristic. So you can see if you're going to use a thermistor, you really have to have something where, let's say you're using it on a variable frequency drive, and you're inputting you're connecting this thermistor to the variable frequency drive. It's going to have to know that whole curve of the particular thermistor you're using in order to know what the temperature is. So some drives actually have a thermistor input, a standard, and we do see this, and we particularly see this sometimes in OEM equipment where they're using the same motor on the same device constantly. This is a thermocouple. Now this is more what you see in your heavy-duty industrial motors. You can see there's lots of types of thermocouples, and they're based on the fact that when you take two pieces of metal and you connect them together here, they are going to create a voltage, and that voltage depends on what the two metals are, and it depends on the temperature of that junction. So there's a lot of them. There's iron constantan, those are the two metals, copper constantan, so on and so forth. We see a type J thermocouple is probably the most common, the iron constantan, but the type K is not unusual, and you really could see any of those things. Now, if you're going to use this, your wiring has to be the same metal as the thermocouple, and you have to have a special thermocouple input on whatever is detecting your temperature. In large motors, this is the most common way to go, and this is a great way to go. This is a resistance temperature detector. So this just says that metals will have higher resistance at higher temperatures. And you could have iron, or you could have copper, you could have nickel, but what I see generally mostly these days is platinum. So the kind of standard that we see is 100 ohm platinum, which means that it measures 100 ohm when the thermocouple, or excuse me, the RTD is at 0 degrees centigrade. Now, I want to mention that this is very important how you hook the thermocouple up. If a thermocouple has two wires, and most of them don't, then you can simply measure the resistance, and that will tell you the temperature. The problem here, as you can see, is you're not just measuring the resistance of the thermocouple, you're also measuring the resistance of the wire between the input of the temperature detector and the thermocouple. I'll tell you experience I had up in Fairbanks, Alaska. We had some RTDs, and they had wired them in this way with just wiring up two wires, but the wire was a long ways. It was probably 300 feet up to the motors, which are in a different part of the building. And they noticed that the motors were running extremely hot. And I went up and measured the temperature of the motors and put my hand on them, and I said, this is not right. They are not running this hot. So I did some investigation and found out that indeed they had wired them with only two wires. And we were measuring the resistance of the wire and thinking that was the resistance of the RTD. And so they showed much hotter temperatures than was actually the case. So what we did was we actually had to buy some new temperature monitors. Didn't buy them new, we had them modified, and used 3 wires. So what you have here with 3 wires is you have 2 reds and 1 white. And this, when you measure the temperature, you put current through here, or you have a voltage across here actually, and then you measure the current, and that tells you the resistance. But you put in another wire and it tells you the voltage right here at the RTD. And since there's no current in this wire, then by looking at the difference between this wire and this one, you can tell what the voltage drop was across the wire. And then you can subtract that voltage drop in the temperature detector, and basically you're measuring the RTD and the wire, but then you're backing out the resistance of the wire. And they're assuming that the resistance of the white will be the same. So you basically take the voltage drop here on red and you double that, because you're also accounting for the white. Now, if you're in a laboratory, you may want to actually have 4 wires, but in motors, the 3-wire setup is very common, and you just need to realize why there's 3 wires and make sure you use them, because there's lots of, you buy a temperature detector, a lot of them will go with 2 wires. And if your temperature detector is close to the RTD and you're not too particular about temperature, that's okay. But be aware that you are going to get higher readings than what is real. RTDs are great because you can actually read what is in the motor. All right, I want to talk a little bit about motor quality. Let's just look at these 3 motors. That's a rolled steel motor. So in a rolled steel motor, we just take a piece of steel, we wrap it in a cylinder, and then we shove the motor inside of it. That is the cheapest kind of motor. The current, or excuse me, the flow of air goes through the motor. So any particulate in the air, oil droplets, whatever, are going to accumulate. You're going to end up with a dirty motor there, even in a fairly clean environment. So these are only suitable for clean environments. And even in clean environments, I would tend to not use them, although they're okay on smaller horsepower sizes. The other thing is that it's very important that the bearings be in alignment. So this steel frame will twist a little bit when you put torque on the motor, and that will cause the bearings to go out of alignment slightly. It's not going to cause the motor to fail right away, but it does have a detrimental effect on bearing life. So the next one up is what we call an open drip proof. Open drip proof, of course, meaning if you get some drips of water on that, it's okay. They won't go into the motor. And open means the air goes through the motor. In this case, we have a cast iron motor. It's better because a cast iron motor is extremely stiff, and a cast iron frame is going to break before it will bend. So it holds those bearings in perfect alignment, and you will get much longer bearing life. And we will talk about bearings in a moment, because those are the #1 cause of motor failure. Now, still in this case, the air is going through the motor, so the interior of the motor is going to get dirty. So the workhorse of American industry is the totally enclosed fan-cooled motor. You want a cast iron frame so that it's very stiff and holds the bearings in alignment, but the air in here, as we showed you earlier, does not go through the motor. It comes in through the end bell. The fan blows it over the outside of the motor, and so this motor will be very clean. I come from the steel industry. You know, I can tell you lots of motors where you weren't sure a motor was there because the dust and dirt and grime, and yet it was still running. Not saying that's a good idea to treat motors like that, but that's why we buy this TEFC. Now, let's say that you go to an automobile dealer and you say, I need to buy a new pickup truck, but I want to make sure I get my best deal. So I want your best price on a pickup truck. And then you go to the second dealer and you say the same, and the third dealer and you say the same. And then you go back and you buy the one who gave you the best price on a pickup truck. Would anybody buy a pickup truck like that? Well, nobody that I know of, because I think you want to know more about that truck than just a pickup truck. You want to know the age of the truck, the manufacturer, you want to know what kind of seats it has, you want to know what kind of engine it has, and on and on and on, because you want to evaluate quality of that truck. Everyone does that, but how many times at your company would somebody say, hey, I lost a motor, and you go to purchasing and you say, I need a 10 horsepower, 1800 RPM motor in this frame size. And what does purchasing do? They go out and they say to 3 distributors and say, give me your price on a 10 horsepower, 1800 RPM motor. And what are they saying to the distributors of those motors? They're saying, please sell me the biggest piece of crap that you can possibly find in the world, because I have no concern about quality. All I care about is a price on a 10 horsepower, 1800 RPM motor. Well, guess what? All motors are not built the same. So let's talk very quickly about what differentiates a quality motor from a motor that is not so good a quality. Well, first of all, there's a stainless steel nameplate, sorry. And the stainless steel nameplate is very important because arguably, if you want to replace a motor or you want to get a motor repaired, when you bring your motor into our repair shop, do you know the very most important thing on that motor is the nameplate, because that tells us what that motor is. If it doesn't have a nameplate, it becomes much, much more difficult. Now, all motors have stainless steel nameplates, right? Wrong. Some of them now have stickers, and that's a shame. And please don't take the motor nameplates off. I know that some people do, and if you know which nameplate belongs to which motor and you're very careful with it, okay. But we had our shop manager used to say there's a special place in hell for people who remove motor nameplates. So you understand how important that is to us. Okay, service factor. Service factor basically says if you have a 1.0 service factor motor, 10 horsepower, it can run at 10 horsepower. If you have a 1.15 horsepower service factor, it can run at 15% over the rating of 10 horsepower. If you have a 1.25 service factor, it can run at 25% over. Now, we typically don't buy those in order to be able to run at higher than nameplate rating. We buy them so that if you have a motor, let's say, that can operate at 15% over its nameplate rating, then at its nameplate rating, it's going to run real cool. And having a motor run cool is really critical. That is one of the biggest things in extending the life of the motor. Extended length iron stack, as we go around this thing clockwise, an oversized copper. The way you know you're getting that is to buy a premium efficiency motors. Premium efficiency motor tends to run at lower temperatures and last longer, in addition to providing energy savings. Now down here we have precision balanced die-cast aluminum skewed rotor bars. You see how those rotor bars are kind of skewed? They're crooked, they're at an angle. Well, that angle basically makes this motor run smoother and gives you more torque on starting. So a smoother motor means your bearings are going to last longer. Now, if bearings are the number one problem or reason for failure, then wouldn't you want to figure out how you can make your bearings last longer? Well, the first thing you can do is use oversized bearings. If the bearings are oversized, they will tend to last longer. Second thing to do is use bearing protection, such as shaft slingers or lip grease seals. That keeps particulate out of the bearing. You want to keep that bearing clean. And if you have dust and grime and particulate getting into the bearing, that is going to shorten the life of the bearing. Next, you can use a cast iron frame motor, which we've already talked about, in order to make sure those bearings are in alignment. And if you will do that, you will significantly increase the lifetime of your motor. And of course, keep the motor running cool. This is inverter duty. We probably are not going to be able to get into that this time due to time. This presentation we're going through is actually a 6-hour training class. So if you want a really good quality motor, what you want to get is a stainless steel nameplate, get a motor with service factor, make it premium efficiency, get precision balanced, aluminum skewed rotor bars, get bearing protection, use oversized bearings, and use a TEFC motor with a cast iron frame. And make sure, because it's TEFC, the air doesn't go through the motor, it goes over the outside. So now if you want to go out and compare prices, that's fine, but ask for something that's quality. Because if you get this quality, it's actually going to last longer and cost you less. Because if you have to replace a low quality motor 3 times in the time that that good quality motor would have continued to run, you just cost yourself more money, not only in the motor cost, but in downtime. One of my customers gave me this, and I think it's good. It's unwise to pay too much, but it's worse to pay too little. When you pay too much, you lose a little money. That's all. When you pay too little, you sometimes lose everything because the thing you bought was incapable of doing the thing it was bought to do. The common law of business balance prohibits paying a little and getting a lot. It can't be done. If you deal with the lowest bidder, it's well to add something for the risk you run. And if you do that, you'll have enough to buy something better. By the way, this is our Galt motor. The Galt motor is a very, very high quality motor. Now, the fact is, none of these are patented. So you can go to any manufacturer, and if he's using all those things and constructing the motor in a great way, you've got a great motor. But this is our standard Galt motor. It's a premium quality motor that just lasts forever. And the first thing that people will generally remark is say, wow, that's a heavy motor. Yes, it is, because it's got 50% more iron and copper in it than a standard motor. And the second thing they say is, go ahead and start it. And we say it is started. It's already running. It is smooth and it is quiet. And that is what's going to make a motor have a long lifespan. Now let's talk about some other enclosures. Then we're going to get into bearings and lubrication, and that's probably as far as we'll get. And then next week we'll get into how you pick a motor for a variable frequency drive. So I've talked about 3 enclosures, and those are the most common, and those are the ones you typically need to know, but there are others. So this is a totally enclosed air over. There's no fan on this thing. And generally we put this thing inside, let's say, the plenum of a heating, ventilation, air conditioning system. If it's in there and whenever the motor's running, the fan is blowing air and air is moving across that motor, then there's no reason to put a fan on the motor itself. So these are used in applications where the motor is mounted inside where the air is already moving, and it will get plenty of ventilation without having an additional fan. This is totally enclosed, non-ventilated. These are great. It also doesn't have a fan, but it is oversized and has the frame is very large so that it can actually stay cool enough just with conduction and convection currents cooling. It doesn't have a fan, and that means this motor is a really heavy-duty motor. The problem is it's going to be a lot more expensive, and generally you don't see these motors much above 10 horsepower because you just can't dissipate the heat. This is a totally enclosed blower cooled. We will talk about, and here's two different mountings. I just thought I'd show you both. Sometimes this is called a totally enclosed blower cooled, or could be called a totally enclosed force ventilated fan or motor. And this is a situation where you have it on a drive and you're running it at very slow speeds. Well, when you run a motor at very slow speeds, the fan on the shaft of that motor is not going to provide very much cooling. And so if you need to do that and the motor is going to run at very slow speeds and very high torques, you may need to add a second motor in order to make sure that you have full cooling at all speeds of the motor. This is weather protective 1 on the left and weather protective 2 on the right. Weather protective 2, the air has to actually make 3 90-degree or greater turns, and that helps get some of the particulate out. And it has an area inside the motor where you have a low air velocity. So what you're trying to do, this is an open motor. It's very difficult in very, very large motors sometimes to cool it. And so you may need to have an open motor in order to get proper cooling. And a WP2 gives you better protection from environmental particulate than a WP1, which does not have those 390-degree turns. This is a totally enclosed air-to-air cooled. Now we're getting into some fancy stuff. You've actually got an air-to-air heat exchanger on there, and you're using a separate fan in order to use that heat exchanger to cool motors. Or if you don't want to use an air-to-air heat exchanger, you can use a water-to-air heat exchanger. And so this would be a totally enclosed water-to-air cooled. This way, the motor, in both of these cases, the motor stays very, very clean and is good for dirty environments. But you have to have a heat exchanger in one case cooled by air, in the other case cooled by plant water. Now let's get into alignment and vibration. We've got about 15 minutes, so we'll do the alignment pretty quickly because alignment is a very specialized, what do I say? You need a fair amount of knowledge really to do good alignment, and most people who do alignments these days do it with a laser alignment tool, but especially on small motors, you can align without that. Let me just point out that when you lift the motor, you want to lift it by the lifting rings, and if a motor has 2 lifting rings, make sure that you use both of them, and you have a maximum of a 45-degree angle here. Here's a vertical machine. Try not to let it tilt, lift it vertically, and use both lifting eyes. This is called a soft foot. You can see in this case, we have a parallel soft foot, and this would be where the motor was actually built with one foot a little bit higher than the other. That's fairly uncommon, but obviously we have a problem there. This would be an angular soft foot, a little bit more common if the motor is damaged and that foot gets bent. And in those cases, what you need to do is you shim and mortar to make sure that those things are level. That is the machine. The foundation is more common the problem. You could have the foundation, as you see over here, different height or slanted. So it's very important that you get a good solid foot on the machine, as a soft foot is going to allow that machine to vibrate and lead to premature failure. We have sent out a brochure. If you didn't get the brochure, please notify Tyler. And that brochure is going to have a lot of really great information from ESA, the Electrical Apparatus Service Association. And this is one of the things in there that tells you, helps you with alignment to show you how accurate you need to be. Now, your alignment, of course, is other than the foot, that needs to be straight and not angled. And if you have a belt on there, it's very important that you have the right kind of bearings to withstand that belt tension, and that the belt be proper, that it not be too loose or too tight. And many times bearing failures are caused by belts that are adjusted too tight. All right, let's get into this. This is bearing protection and bearing lubrication. This is a ball bearing. Now you'll notice it goes around, and one of the things that this one is a spherical roller bearing. You can see a little more expensive, and this will tolerate misalignment a little bit. This is a tapered roller bearing. A tapered roller bearing allows you to have good radial force, but also can support some force in the axial direction. Here's thrust ball bearing, spherical roller bearing, and a fluid film bearing. The fluid film bearing, it's sliding. The whole thing is sliding, and typically these are in oil baths. L10 life. The L10 life is the number of hours in service that 90% of the bearings will survive. And so we typically like to see an L10 life of about 50,000 hours for larger motors and 20,000 hours for your smaller motors. Now, this is interesting. If you look at the bottom, this is not from me. This is from a bearing manufacturer. In a perfect world, if ball bearings were kept clean, cool, well-aligned, and properly lubricated, their average L10 life should be 350 years. Few bearing failures are the result of true bearing steel fatigue. Most failures are caused by improper bearing use or inadequate maintenance, and I might add excessive temperature to that. This is from SKM, a bearing manufacturer. It shows some of why bearings fails, and they're saying that lubrication failures are responsible for most bearing failures, and bearing failures are the #1 reason for motor failure. These are functions of the lubrication. You can just try to scan that, and again, you will get a copy of this, or you can download a copy of this once we post it online. So I'm not going to spend a lot of time with that because I want to talk about some more interesting things. You notice that even though the races look smooth, they're not terribly smooth, and so you need a lubricating film. Up to 80% of motor failures originate in the bearing, and improper greasing is a common cause of bearing failure. So that's what I want to talk about, is how to grease a motor. You might guess that these motors have been improperly greased. If that's your guess, you would be correct. Now let's talk about how to grease a motor. Who greases motors? Well, sometimes you have really good quality, smart people that grease motors. But I would say that too often the guy who greases the motor is the new guy. Why? Because nobody wants to grease motors. It's not a fun job. And so the new guy does it, and the new guy doesn't know how. You get improper greasing, and you have premature motor failure. One of the most important thing you can do in your facility is to have a proper bearing lubrication program. So this is, in general, a good recommendation for how to grease a motor. Number one, ideally the grease in the motor should be at operating temperature. You can't do that all the time, but it would be really great if you could shut a motor down while it's hot and grease it right then. Number two, remove the Zerk cap and the drain plug. Number three, clean the grease fittings. Very, very important. If you just stick your grease gun on that grease fitting, it's going to have little pieces of rock, grime, particulate, and you're going to push those right into the bearing. So not only clean the grease fitting, please clean the grease gun. And make sure that what you're putting in there is clean. I can't emphasize that too much. That's one of the most common problems we get. Pump the grease slowly and carefully. Please pump grease slowly. It takes time for it to flow through the bearings. If you pump it too fast, you may pump it out the seals, or it may not go through the whole bearing. Keep pumping until grease comes out the drain. Now remember up there in number two, we need to remove the drain plug. If you don't remove the drain plug, you are simply pushing that grease through the seals and into the middle of the motor, into the air gap, and it's going to have premature failure. So you wait till the new grease comes out of the drain, then you rotate the motor by hand if possible, and wait until grease comes out of the drain. Don't put the drain plug on right away. I'll show you why in a moment. Run the motor for a minimum of 30 minutes until the grease stops coming out of the drain. Then go ahead and clean those grease fittings, reinsert the cap on the drain plug. This is a little more difficult than the way a lot of people grease the motor, but if you want it to last a long time, you'll want to use that. How much grease do you use? Well, this is a formula, and if you want to look at the bearing diameter and so on, you can use this, but typically people don't do this. Most people who grease motors don't like to sit and do formulas. So mostly we just pump it until clean grease comes out. Remember that not all grease guns have the same amount of grease per pump. Now, how much grease should you use? Well, again, I showed you that formula, but the best way to know that is on the motor data sheet. The next best way is to just wait till the clean grease comes out. Now, look at that motor. Grease is a holder. Grease does not lubricate bearings. Grease simply holds the oil so that the oil can lubricate the bearings. If you have too much grease in there like that, and this is what it may look like after you grease it, then it's going to be like swimming or like trying to walk in a swimming pool. You get this churning, and that bearing is going to get very hot. And so that's why it's very important to open that drain plug and allow that grease to come out. Now, this is a picture of the inside of a end bell here, and you can see that here's your Zerk. When you pump, it has to go through this tube here. So when you start pumping in, it's not going into the bearing at all. It's just going through the tube that leads to the bearing. Then it goes through the bearing, and after it gets through the bearing, then it goes out the grease drain. And in this particular one, it has 2 grease drains. So make sure that those drains are open when you lubricate and open when you run the motor, and allow that grease to come out before you put the plug back on. This is a shielded bearing. We don't have too much time to get into shielded bearings, but they're double shielded or triple shielded, and that helps keep the grease in there. Even with a shielded bearing, notice that the grease still moves because there's still a little gap there, and the grease by centrifugal action will go out. It'll come out here, and then it'll go around through that grease cavity and back in. So there is some grease movement in a shielded bearing like that. This is a sealed bearing. There is no movement. Sealed bearings seem really nice because you never have to grease them, right? But they're only appropriate for lower speed motors. And sealed motors are generally used only 75 horsepower and under. And if you run a motor pretty much 24/7, you can expect a sealed bearing to last about 3 years because you can't re-grease. So if you want a bearing to last much longer than that, you should get a re-greasable bearing. Now, this can be the last thing I talk about. What is the rule of thumb for how often to re-grease a motor? And the answer is there's no rule of thumb. It depends on some factors. So what I'm going to do is take you through 5 ways of determining this, and you can pick which one you want to use. So number 1, this might seem like a cop-out, but it is not. This is very important. If you have a motor data sheet that tells you how often to re-grease that motor, that's the best information you're going to get. So that is the best way to do it. Now, if you don't have that, or you don't want to use that, here's number 2. This is actually on the data sheet for some grease manufacturers, Exxon, Chevron, and so on. And if you take 14 million divided by the shaft RPM divided by the square root of the bearing ID minus 4 times the bearing ID times F for the bearing type times F for the temperature times F for contamination, it can tell you the frequency. I have a problem with this, number 1, because who's going to do it? And secondly, I have a problem with this because you're probably going to get the calculation wrong. And if you just get one thing wrong, like the F for the bearing type, it can totally mess you up. So I don't know why anybody would do this, but I'm putting it in here because it comes with your grease and it tells you you can use this formula. And I don't doubt that the formula works. In order to do it, you need to know the bearing diameters, and generally the small d is the bore diameter, or basically the shaft diameter, or the inner race diameter. The large D is the outside diameter. How often do you re-grease? This is number 3. This is a much better way to go, and it's included in the booklet that is included with this class. So I'm just including a couple of curves. And so over here, you look at, do you have a radial ball bearing or a cylindrical roller bearing? I'm going to, oh, I don't have my, let's see. There we go. We've got some red lines that'll help you out there. So first of all, I look at my speed on the bottom. Let's say I got an 1800 RPM motor. I go up and I have to find that little d. Now, what is that little d? Well, typically, if you have a 313 bearing, you take the 13, the last 2 digits, multiply that by 5, and that's 65 millimeter. So we're going to go up to 65 millimeter. Then we're going to go to the, we're going to go to the left. And if we have a radial ball bearing, we should re-grease about every 6,000 hours, about every 9 months. If you have a cylindrical roller bearing, you should re-grease twice as often as that, probably 3 times a year. Remember, there are 8,760 hours in a year. This is a really good way to do it. I like this way to do it, and it is, again, is included in your book. So it's very simple. You're not likely to make a mistake, and it's very good, and it gives you some feel for how often motors should be lubricated. This is a similar deal, and I won't go through it completely, but it gives you an example of a 6210 ball bearing. You take the 10 times 5, it's 50 millimeters, and then you find the speed of your motor. You go up to the 50 millimeters, then go across. And in this case, it has 3 on the left, a radial ball bearing, a cylindrical roller bearing, and a tapered roller bearing. So many manufacturers put out these little curves. Doesn't matter which one you use, they're all very good. Number 4, how often do you re-grease? You can do it by a table. And here's a table. You look at the RPM, the frame size, and then are you running 8 hours a day or 24 hours a day? And it will give you the re-greasing intervals. I think that's not a bad way to do it either. And you can see that most re-greasing intervals run from about 4 to 12 months. And number 5, this will be the end for today. And this is how, for instance, some farmers do it. Farmers simply grease all their motors at the beginning of each season. And that may be enough, or it may not be enough, but that has been a common thing. And in a lot of cases, it works. If you have high temperature, high speed, dirty environment, or a 24/7 operation, then sometimes you can use maintenance records and actually determine how often they need to be testing on the basis of measuring the vibration or looking at the temperature of your bearings. Or you can use annual or simply semi-annual greasing. And a lot of people do this, but I would really uh, recommend that you use number 4 or number 3 here where you have these curves. So I've got about 3 minutes over. I apologize, but I think lubrication of bearings is extremely important. And a lot of people just go out there and pump a few squirts in there and they're done, and they may not even remove the drain plug. This is really critical stuff. This is maybe the most important thing you can do to ensure the life of your motor. So I am going to stop there and we'll turn it back to Tyler.
All right, let's go through a couple questions here. The first that we see is the last 2 number calculation for bearing ID a standard for all bearing manufacturers?
Yeah, that tends to be a standard for all bearing manufacturers, at least NEMA bearing manufacturers. Now, I can't say from around the world, but for your smaller bearings, this doesn't work if you've got a 10,000 horsepower motor. But for your smaller bearings, this is pretty standard amongst all the manufacturers, and this is a bearing thing more than it is a motor manufacturer thing, and the bearing manufacturers do adhere to that.
Great. Do all TEFC motors have a drain plug?
This is a good question. First of all, you can have a TEFC motor with a sealed bearing. If it has a sealed bearing, no, it's not going to have a drain plug because you can't re-grease it. So there are a lot of TEFC motors that have non-regreasable bearings. I've also seen some motors, and people will say, look at this motor, you know, it's got this Zerk fitting, but there's no drain plug. And I kind of scratch my head at some of those things. And so in some cases, you may have to go back and check with the manufacturer and find out what's going on there. Because if you have a Zerk fitting to put grease into the motor, you have to have a drain plug. Otherwise, where's that grease going to go? But it can be an issue. We have an ISA Motor Shop. We have one in Boise. We have one in Pomona, California. We've got one in Salt Lake. We've got one in Rock Springs. And if you have those types of questions, you can certainly call those people that deal with motors every day, day in and day out, and they may be able to help you if you really cannot find the drain plug.
Does using a VFD void a bearing warranty?
Using a VFD certainly does not void the bearing warranty. We do this all the time. Now, having said that, next week, we are going to talk about bearings on variable frequency drives. And we do recommend, if it's a critical application, that you provide bearing protection. And it may be that a bearing manufacturer will say, I'm not going to warranty that bearing because it's got pitting, and the reason is you didn't put bearing protection on. So tune in next week for that, and we will get into some pretty good detail on how to do bearing protection. ISA recommends that on every motor you use bearing protection, and this is something that is not in the bearing. It is used to prevent currents going through the bearing, and those are typically shaft grounding rings or insulated bearings. So that's about all the time I have to talk about that right at the moment, but we're going to spend a lot more time on that very subject next week.
How does a motor fail at high temperature? For example, if it is decided to bypass a temperature safety feature, for example, you have a bad RTD or whatever reason, what do you expect to see just before and just after a motor fails?
Yeah, so if you have, we tend to talk about motor insulation, and so that takes time. You don't have a high temperature and in 2 minutes the insulation fails. But if a motor is running at high temperatures, then you can see an insulation failure. It could be a turn-to-turn fault, or it could be a turn-to-ground fault. And you can generally measure those simply by measuring the motor to see if you have an insulation issue. However, if the motor really runs hot in many cases, it's not going to be the insulation that's going to fail first. It's going to be the bearing. And so when the bearing fails, a lot of times the grease gets too hot, it runs out, doesn't have proper lubrication, and we end up with just more friction in there, and the bearing gets hotter, and then that more oil runs out, more friction, and that causes it to get even hotter, and pretty soon you end up with vibration in that bearing or noise in the bearing, and of course by that time it's a little too late. But those are typically the places where you're going to see high temperature failures on a motor, is either in the insulation or in the bearings.
What enclosure types are needed in environments with explosive gases?
Oh, thank you. We didn't cover that, and that would be a good thing to cover. So it depends on what the explosive gas is, and this answer has to be necessarily brief because of time. But in most cases, if you put, it depends on whether the explosive gas is there all the time, or just it could be there part of the time. And so in most cases, like in the oil field, this is very common. It could be there part of the time. So first of all, you need to know what the gas is. You need to know what the ignition temperature of the gas is. Then in terms of the motor, you must first of all have a non-sparking fan. In general, that's a plastic fan. If that fan is a metal fan and hits some metal part and sparks, obviously that's going to create an explosion. Then you need to make sure that the motor temperature does not reach the ignition temperature of the gas. And then finally, you have to have an explosion-proof motor. Now, an explosion-proof motor does not prevent an explosion. An explosion-proof motor says that if an explosion occurs inside the motor, then the flame path out from the motor to the outside through the end bells there has to be long enough to where you won't end up with a flame coming out of the motor and igniting an explosion on the outside of the motor. And so that's the most common thing we see. And so you need to know whether it's a gas or flammable fibers, and then you figure out what the gas is and what class it is, and whether it's there all the time or not, and then you can find the motor. And sometimes they don't build motors for certain types of atmospheres. But that's typically the way it is. And an explosion-proof motor typically has to be UL. Most motors are not UL listed, but explosion-proof has to be. And I know our motor shop is qualified to work on UL explosion-proof motors.
Is it recommended to do body earthing on all types of motors?
Yeah, so when we talk about earthing, I think here we got a European, but maybe that's getting more common in the US. So in general, in the United States, we talk about grounding, and that means connecting some conductive part to the earth. In Europe and other places, they call that earthing. It's the same thing. Not only is it recommended that you connect the frame of the motor to ground, it is a National Electrical Code requirement that you connect that frame to ground. So all frames of motors must be grounded or must be earthed. And the reason for that is if they're not, and you have a conductor accidentally touch the outside of the motor, and then somebody comes along and puts their hand on the motor, they could get electrocuted. So you always must ground the frame of the motor.
Why is residential electrical standardized as single phase and not three phase?
Yeah, now this goes back a long ways, and there are a couple of answers to that. One of the things I'll mention is if you have a dryer, you know, there are 3-wire dryers and there are 4-wire dryers in your house. And with a 3-wire dryer, your neutral and your ground are connected together in the dryer. And you'd say, well, why would we do that? I mean, that's kind of a no-no. We always separate the neutral and ground. And the reason they did that is because during World War II, we wanted all the copper we had to make munitions. And therefore, we decided to do that to save one conductor and save the copper. I understand that's history. That's the way it went, but it's not a good way to go. And so I know I have some rental units. Whenever I see a 3-wire dryer outlet, I convert it to a 4-wire dryer outlet to keep the neutral and the ground separate. The reason I mention that is if you have your wires into your house, you got 3 wires. You're going to have your phase, your hot phase on one side, your hot phase on the other side, and your neutral, and then you're going to have your ground also. And if you had 3-phase, then of course you'd have to have 3 wires plus a neutral plus a ground. So now you have 5 wires. So you saved 1 wire there. That's one of the reasons. The other reason has to do with the transformers. 3-phase transformer is more expensive. Now, whoever asked that question, I kind of think, what would have happened if we had done that? What would have happened if we had brought 3-phase to a house? In some ways, I think that would have been a wonderful thing because 3-phase motors are so much better than single-phase motors. But remember that in your house, typically in your outlets and so on, you only bring 3 wires. You only bring 1 phase if it's 120 volts plus your neutral plus your ground. And if it were 3 phases, you'd have to bring 5 wires. So there certainly is some wiring savings that goes along with that, and that's your primary reason for going single phase.
Someone changed out a motor on a ventilation fan years ago, and I suspect the motor may be the wrong horsepower, RPM, etc. How do I determine the correct size motor?
Yeah, so great idea. The main thing I would say, going back to nameplates, look at the nameplate. And you want to get a motor that is the same horsepower, the same speed, and the same voltage. Now you might say, oh yeah, but it doesn't have a nameplate. Well, that's when it gets a little squirrelier, because there's no way that you can just look at a motor and know what speed it should have been. So I will say the first thing you want to do is you want to get the right frame size. That's mostly for fit, to make sure the thing fits in there. But then recognize, and I think we covered this last time, you can look at the current in the motor, and the current is a representation of torque. So if you've got too much current in that motor, and we're not using a VFD on it, you have too much torque, and that means the motor's too small for the speed that it's running. That's a pretty easy way to measure by simply looking at the current, and the current will tell you how much torque is there. And you want to be under the full load current of the motor. Otherwise, you really need to go to a higher horsepower motor. Now, if you put a different speed motor in there, then of course, if you had a 1200 RPM motor and you put in an 1800 RPM motor, you're going to need 4 times as much torque, and you're going to be way too small on your motor. So I would say that's a little more difficult because you have to look at your airflow. And if your airflow just isn't what it used to be, you probably put in a motor that is too slow a speed. If your airflow is way higher than it used to be, or your currents are just way out of line, yeah, you may have put in a motor that is a higher speed than it should have been.
Great. That's all the questions we have today. So we'd like to thank everyone for joining us and invite you to attend the next part and the final part in getting the most from your electric motors.